Hello, welcome back. Okay, now we're going to be looking at some special kind of diode, okay, in which we are going to be talking about a diode known as Zener diode. Right? What is Zener diode and what is it used for? Now, first, a Zener diode is a diode that is operated at a reverse bias mode. We already know that a diode is supposed to be forward biased, okay, where it will only allow current to flow through it. If you reverse bias it, current doesn't flow through it, okay, but if you actually increase the voltage, the reverse bias voltage, what happens? You destroy the bonding of that particular diode of the semiconductor, then it current now flows. So now Zener diode is always operated in that mode. Okay, so any place where it finds itself in a circuit, in any electronic circuit, it must be operated in a reverse biased mode. Okay, and not just in reverse bias mode, at the breakdown mode. Remember, the breakdown voltage is a voltage that current can, there's only voltage, okay, it's only point where current can actually flow through the the diode, okay, in a reverse bias mode. Now, also know very well that what actually causes the breakdown of the diode when it is being reverse biased is due to heat. As you increase the reverse bias voltage, the diode actually heats up, okay, which eventually causes the bonding of the semiconductor to be broken. All right. So which simply means that a diode is another diode that is actually operated at reverse bias mode must be actually be chosen. That semiconductor must be chosen to handle, okay, temperature, to be able to handle high temperature. So it must be a semiconductor that can handle high temperature. Why? Because in a reverse bias direction, that diode always heats up. Okay, so now this is the VI characteristics. Okay, current voltage or IV characteristics of diode. So the same characteristics graph we drew when we actually illustrated the reverse bias diode, that is what we have here. But in the case of Zener diode, okay, that current, the minimum current that current flows, where you have the reverse saturation current or the leakage current, we call it the minimum Zener current, okay. And of course, the maximum current that can actually flow after the breakdown, we call it this is the IZ, maximum Zener current. Then the VZ is the breakdown voltage we normally know, okay, in a regular diode. That breakdown voltage we call it, in this case of Zener diode, we call it Zener voltage, right? So we simply mean that a diode must be operated at the point where the supply voltage, okay, must be equal to the Zener voltage. That is when you now have current flowing through it. Now, one good thing, one useful application of a Zener diode is that it's used as a voltage regulator. What do I mean by voltage regulator? You remember, as you can see from this graph, at the point where the diode actually reaches the breakdown or the Zener voltage is being supplied to that diode. The Zener voltage, even though it's still the same voltage at, okay, the same voltage you see, Zener voltage is what you have between the maximum and of course minimum current, okay. Please pardon me from my graph. The Zener voltage is not really, the Zener voltage is chosen that is not really at the, okay, the minimum is not really at that reverse saturation current. So let's this reverse is somewhere around here, okay. There's a little difference between the reverse saturation current, the leakage current, okay. So somewhere around here, that's where we have the minimum Zener voltage, Zener current, okay, in the graph. So please take note of that. All right, and correct that. Okay, so all right. So with what we have now, we now see that from the current of the minimum Zener current to the maximum Zener current, we still have the same voltage. So that means we can use this as a voltage regulator. No matter what current that flows between this region from here to here, okay, the Zener will always have a steady Zener voltage. A steady Zener voltage, okay. So even though you supply more voltage to the Zener diode, at the point in as much as it's operating at this particular region, okay, it will always deliver this constant Zener voltage within this range of current, IZ minimum and IZ maximum. That is why we say that a Zener diode is always good as a voltage regulator to give a constant voltage, output voltage to the load. Alright, so now let's look at some equivalent circuit. Okay, now some schematic diagram of Zener diode, how it is being connected. Okay, so let's look at a simple case where I should connect this 6 volt battery. Okay, then across this one of me. Okay, so let's do this. Now for a Zener diode, okay, the electrical symbol of a Zener diode is this is what you see, unlike what you have. Okay, you have this for a diode, but this is how it is for a Zener diode. So they kind of Z after the arrow. So once you see that symbol, you simply know that we are actually dealing with a Zener diode. Okay, so I hope that is well understood. Alright, now there is something I could actually connect. Okay, please follow me. Okay, I connect a resistor in series to actually limit the current to some extent. So I connect the resistor. Let's say I have a resistance of 500 ohms. Okay. Now this diode, Zener diode, look at the characteristic. The VZ of this Zener diode is 10 volts. Okay. And of course the I maximum of the Zener diode, the maximum amount of current it will take is 6 milliampere. So the question is, if I should supply a voltage of 6 volts to this value diode, this Zener diode, do you think it will operate? Will you function? Now first of all, let's look at the connection. Okay, you remember a Zener diode should be reverse biased. So this diode is reverse biased. Yes, it is reverse biased. The anode is connected to the negative terminal of the battery, and the cathode is connected. But there's one thing: this diode will not be operational. Why? Because the supply voltage is less than the Zener voltage. Okay, before the breakdown, the supply voltage must be equal or greater than the Zener voltage. So in this case, this diode would definitely, the Zener diode would not act like an open circuit. This will not work. All right. This particular Zener diode that is connected will not work, so it will not deliver current. Current will not flow through it. But a situation where, let's say, I have a supply voltage of 12 volts. Okay, with 10 volts Zener voltage, and of course the same maximum Zener current of 6 milliampere. Then you rest assured that current will flow through this Zener. Okay, now the current that will flow through this Zener, you discover that it is this maximum current that will flow through the resistor that we have here, resistor of 500 ohms. So now let's see exactly. Oh, please pardon me. This Zener current, still this Zener current is not the current flowing through the resistors. This is the maximum Zener current. Okay, show you the maximum current that the Zener could actually take before, right? It actually shuts down. If you take more than this current, it will shut down. So this is the maximum Zener current. The maximum Zener current. Okay, so now what we're looking at, we want to find out the current that is actually that's going to flow through this 500 ohms. Of course, from our analysis, the 12 volts supplied, okay, is going to be equal to the voltage across the Zener, which of course is 10 volts. It's always a constant voltage, then plus the voltage across the 500 ohm, which of course is going to be the current across the 500 ohm. All right, the circuit current, then multiply by the resistance of 500 ohm. That way now I can be able to get that current. So the current across this 500 ohm is going to be equal to I. It's going to be equal to 12 minus 10, then divided by 500. Okay, so you end up having 2 all over 500. So if you divide it, that's going to give me 0.004 ampere, which should be 4 milliampere. So this is the current that's flowing through this 500 ohm resistor. All right, let's look at another circuit diagram of a Zener diode, then we analyze it. Okay, so let's look at a situation where a voltage source of this time around 18 volts, so is connected, okay, across resistor of 600 ohm, 600 ohm. Then across another resistor of this one is R1. This resistor is R1. Why this one is R2? Okay, so this one here is 1800 ohms. Then across the resistor R2, I'll connect a Zener diode. Okay, I'll connect a Zener diode whose Zener voltage Vz, okay, is equal to 12 volts, and the maximum current Iz. So this is actually when this Zener voltage, okay, is called the rating of the Zener. That is the voltage that the Zener must take before it operates. And once it takes this voltage, then it will remain at this voltage throughout this current. Okay, so that means simply that once you be able to supply this this voltage 12 volt to this Zener, okay, then definitely you have this steady voltage across the Zener. No matter whatever supply voltage, no matter how much you increase the supply voltage, this voltage is what you have across that the Zener will deliver, okay, across the Zener. The only way this voltage will change is if you actually exceed the maximum current. Okay, if the current passing through the Zener exceeds its maximum current, that is the only way the voltage will change. But in as much as the supply voltage is 12 volts, okay, of course within the limit of Iz minimum, okay, and of course Iz maximum, this Zener diode will always keep constant its voltage rating. Okay, so I hope that's well understood. So now the question is, from this circuit diagram, is this diode biased well? Yes, let's check the connection first. Of course, the cathode of the Zener diode is connected to the negative, correct? And of course, the other to the positive. So the connection is correct. Now the question is the voltage supplied to this diode, is it enough to actually cause this diode to operate? How do we know the voltage? So the voltage that is supplied to this diode is actually going to be the voltage across this R2. So this is a voltage divider, of course you know that. So this supply voltage will divide between R1 and R2. Okay? To divide between R1 and R2. Of course, we all know how we've actually talked about voltage divider. Okay, when we did at this the introduction to circuit theory, you did voltage divider. So let's get the voltage across R2. You know how we do it. Voltage across R2, let me call it V2, is going to be equal to the entire voltage, or the the resistance of R2, which is of course is 1800, divided by the total resistance. Okay, the total resistance is actually 600 plus 1800. 600 plus 1800, then multiply by the supply voltage. Okay, the supply voltage, which is 18 volts. All right, so let's do this. 1800 plus 600, that should give me 2400, right? So I'm having 1800 divided by 2400. 1800 divided by 2400, that's 0.75. Okay, then of course multiply by 18 times 18, 13.5 volts. So V2 is 13.5 volts. Now, seeing that the Zener voltage of this diode is 12 volts, that simply means that the voltage is enough. Okay, it is enough to actually operate this Zener diode. Okay, at the at a reverse bias mode. All right. So this is the voltage I supply across the Zener diode. But even though this is the voltage that is being supplied, the Zener diode will still maintain its uh, constant voltage, which of course is 12 volts. So that is why we can say that a Zener diode is used as a voltage regulator. Okay, so please, actually, you have to take note of this. And I think, what do I need to get again? Okay, I will have to, let's see the current. Okay, with this voltage now, let's see the current that is actually flowing through the Zeners to see whether that current is above the maximum current of Zener diode. How do I get the current that is going through the to this Zener diode? Okay, so let's say the current that is going through R1 is I1. Let me call that I1. Let's look at the current. Of course, when this I1 reaches this point, it actually branches. So let's look at the current going through the Zener diode. Let me call it IZ. Okay, let this one be IZ maximum, the rating. Let me just call this IZ. Now let the current enter into R2, okay, be I2. So of course, according to Kirchhoff law, the current that is entering into a node, this is the node, okay, is equal to the current that's leaving the node. So now I1 is entering to the node, both IZ and I2 is leaving the node. So I'm gonna have I1 is equal to IZ plus I2. My whole idea is to get the IZ, okay? So IZ now is going to be equal to I1 minus I2. All right, so how do we get this current I1 minus I2? Okay, so that's exactly what we are going to discuss. So we're going to be, in the next video, we are going to talk about how we actually get our current, to be able to know if this current supplied to the diode is within its range, okay, or it is not. Then we'll also look at how a diode is used as a voltage regulator. So I will do that in the next video. Thank you very much.